Project 2.3, Unpacked, the 555 timer. This is the final device with all of the 6 applications. This is the 555 oscillator, and it showcases the 555 timer in astable mode, where there's not a stable state and the chip continuously switches its output between high and low. This output is displayed via an LED. This is the unpacked 555 oscillator, which shows the internal components of the 555 chip. It features 3 resistors of equal value that divide the voltage, 2 LM358 op amps used as comparators, a 4001 NOR gate used to make an SR latch, an NPN 3904 discharge transistor, and a 4069 NOT gate to invert the output. This is a Fallstad diagram of the 555 unpacked oscillator. When the capacitor charging the trigger pin goes above 1/3 VCC, now the inverting pin is larger than the non-inverting pin, so this goes low. The other input is already high from the previous action, so the SR NOR latch continues to output low, which is inverted, so the LED stays high. Once the capacitor has reached 2/3 VCC, now the non-inverting pin here is higher than the inverting pin here, which means that the top comparator goes high, which means that the output of the top NOR gate goes low. Now this will output a high, the bottom comparator will output a high, and that will be inverted, so the LED is now low. Eventually, the capacitor will discharge to 1/3 VCC and the SR latch will switch again. The capacitor begins charging again and the LED output goes high. The astable 555 will continuously oscillate between these two states. This creates a continuous digital square wave output, which is displayed using an LED. This binary and decimal countdown circuit simply takes the 555 oscillator's output and uses it as a clock signal, for which each high-low cycle adds to the count by 1. A 4511 converter is used, which takes the binary output from the 4510 and converts it into decimal using the 7-segment display. The benefit here of the 555 is using external components. We can program the circuit to oscillate at 1 Hz, meaning the circuit counts down every 1 second. By choosing capacitor and R1 values, we can solve for R based on the frequency we want. The math for this is shown on the right of the screen. Here's our 555 tone generator. I've changed the resistance and capacitor values from the original oscillator to create a square wave frequency of 2 kHz to power our piezoelectric buzzer. The math is shown on screen. Our piezo buzzer takes advantage of the piezoelectric effect, where certain crystalline metals whose internal atomic structure lacks a center of symmetry because the positive and negative charges inside these crystals do not perfectly overlap on an atomic level, mechanical stress can shift them. When the crystal is bent, tiny displacements of the atoms cause charge to accumulate on its surfaces. This produces a measurable voltage. This also applies in reverse, so when we apply changing voltage in the form of a square wave, the material deforms and pushes air, creating a sound waves at the same frequency of the oscillating signal. This is the 2 kHz frequency outputted by the piezoelectric buzzer. To fully understand the 555 timer, we must also explore how this chip can be used in monostable and bistable mode. This LED timer shows the chip in monostable mode, where there is only one stable state. When the PBNO is pressed, the capacitor starts to discharge and the output flips high. When the capacitor discharges, the circuit restores its idle position and the output returns low. The monostable 555 timer only has one stable state. In the stable state, the timing capacitor is fully discharged. Pin 2 is being held high by the pull-up resistor, and the output pin 3 is low. The discharge transistor inside the chip holds the capacitor at ground while keeping the circuit stable and waiting. When the PBNO is pressed, the button momentarily connects pin 2 to ground, pulling it low. This drop below 1/3 VCC causes the 555 to trigger, which immediately makes the output go high. This releases the discharge transistor so the timing capacitor can begin charging. This drop below 1/3 VCC causes the 555 to trigger, which immediately makes the output go high and releases the discharge transistor so the timing capacitor can begin discharging. The output stays high for the full timing interval set by the resistor and capacitor. After the capacitor charges to 2/3 VCC, the 555 returns to its idle state, the output goes low again, and the discharge transistor turns back on. This memory latch displays the 555 timer in bistable mode, where it has two stable positions. Essentially, the two PB&Os are connected to the SR latch set and reset inputs. When the left PB&O is pressed, a 1 is outputted and stored, even after the button is no longer being pressed. The right button likewise will output and store a 0. This circuit essentially functions as a 1-bit digital memory, which shows how sequential circuits can store information. For the bistable 555 memory latch, when the left PB&O is pressed, it essentially drives the lower comparator, the set comparator, high. First NOR gate outputs a low, which means that there's two low inputs on the bottom NOR gate, which outputs a high. So then even after the PB&O is released and set goes low, it holds this value. When the reset pin is hit, it flashes high to the lower NOR gate, which causes this to output low, which then means that the upper NOR gate now has two low inputs, which means it'll output a high, and it'll keep the output at low. Whatever state was last inputted is held even after the input is no longer high. This is the basic idea behind digital memory and sequential circuits.